All right, so today's lecture is going to be of a similar style to Monday's. We're going to be talking about logistic regression today, as well as its interpretation and something called cross-validation, which is, in my opinion, a better version of the validation method that you guys were introduced to on Monday. So hopefully this won't take too long, especially because we're not going to be going over the proofs or statistics on getting the betas or the covariance matrix from for logistic regression. And the overall point of really of learning about this model is that you can get a very high level understanding of how it works, because it becomes very important when we're talking about binary outcomes.
Oh, make sure you sign in, by the way. I don't know if we missed
anything. Oh yeah. So yeah, sign into that tiny URL if you just came in. And okay, so yeah, outline for today, we'll talk about the model, where it comes from, how to interpret the model. Finally, and this is something that I probably should have talked about probably on Monday or before Monday, how to deal with categorical data. I just couldn't figure out the best time to put this in other than today. So we'll talk about how to deal with these kinds of data when we're running the model on the Titanic data set, as well as when you're running the model on the house price project. And then finally, we'll talk about K-Fold's cross-validation. So importantly, the difference between linear regression, the regression model that we had on Monday, and our model that we're going to be learning today is really the outcome of the data. So before, the outcome was college GPA, which was more or less a continuous sequence of numbers. You can have like a GPA of 3.1385, etc. in theory, and you'd be fine with it. But for other problems, it's more of a class type problem where you're trying to predict something that belongs to a particular class. Like for example, spam or ham. Those are two particular classes that you want to try to predict, which is not continuous, and so it lends itself to a different sort of problem than the regression type problem that we had before. So this is another example, a very similar example really, of where we have a bunch of predictor variables that's trying to predict whether something is spam or not. And the right side is the graph, or a very simplistic graph of what it might look like. And as you can see, if we try to do the regression model that we learned on Monday, we'll be drawing a line that's basically very similar to that. But does anybody see any particular problems with that line? Yeah. Sorry, say it again? Yeah, so it'll cross over the maximum, and also it'll go below the minimum value, which is 0. And this is something that we don't really want, because technically, if we run a regression model, we can have like a value of span that is like 1.5, or a value of span that's 0.5, or negative 10, and that's pretty meaningless. Instead, what we want for this type of problem, and more naturally too, is that, well, if we're trying to predict whether something is 1 or 0, then we can formulate this as like the probability of something that is 1 or 0. And so ideally, we want a model that can spit out some kind of response value, or our response value y, to be bounded between 0 and 1. And so this motivates a different type of model called the logistic regression model, which is basically very similar to the linear regression model that we had before. So if you look at the board, look at the slides, you see a lot of variables flying around. But basically, it's just a transformation of our linear regression model that we had before to be slightly different. And so the transformation up there, e to the beta naught, etc., over 1 plus e to the beta naught, etc., will actually bind our response values to be between 0 and 1. And in order to, I guess, motivate why this works, I have like a couple questions for you guys that should not be too hard, I imagine. So the first question is, what is p of x when that line is equal to 0? Just like a food for thought kind of question. Anybody have an answer to that? So if you just replace the beta naught plus beta 1, x1, etc., with just the value of 0 in the logistic regression equation, what output do you get? What does p of x equal to? Yeah, 1/2, right? Great. So then what about 100? when that line becomes 100. It'll be basically 1, right? So as that value goes to like ever larger values, basically the numerator and denominator are essentially the same, and then p of x will be approaching 1. All right, good. How about negative 100? And 0, right? Yeah, so e to the negative large number will tend to 0, and that would basically push p of x to the value of 0. And so basically, you can probably convince yourselves that this transformation does the job for us. It's not just any kind of transformation, it's specifically this kind, where we combine our values that we predicted before to be between 0 and 1, which lends itself naturally to the concept of probability. And so this is a graph of what that will look like for this particular case, which is, wait, I can't read that. Oh yeah, this is the probability of passing an exam on the y-axis. And so this is like a binary problem. You pass the exam or you do not pass the exam. And then the x-axis is the number of hours of studying. And so basically, when we convert our regression model to a probabilistic model, logistic regression model like so, we would get this nice curve, this S-shaped curve, where it's essentially bounded between 0 and 1, and also the previous response value of 0 would be basically at the 0.5 probability mark. So yeah, any questions about that so far? So this is just basically a very high-level overview of why we want to use a logistic regression model and how it will look like. Yeah.
So why is it different from linear regression?
Yeah. So yeah, the exact difference is that it predicts between 0 and 1, whereas regression models, it can predict any kind of continuous value. So for example, the housing project, you have house prices between 0 to whatever the maximum number is, and essentially any number in between is fair game. Whereas for a binary classification model, we only want to predict between 0 and 1 only. And the natural way of thinking about it is to see how likely it is to predict something that is 1, and how unlikely it is to predict that something as 1. And like when we spit out probabilities, like say 0.6 for example, then anything greater than 0.5, like we're just assumed to be 1, and anything lower than 0.5 we're assumed to be 0. And that can change, but that's just like a natural way of converting the probabilities and back into classes. So, any other questions? All right, cool. So how to get beta? This is just, again, a very high-level approach of one way to get beta. Unfortunately, there is no closed solution for this, which is why like it's probably not a good idea to go over like exactly how you're going to find it. But the approach that probably the most common approach to getting the betas for a logistic regression model is using a method called Newton-Raphson method, which probably some of you guys have seen before, but if not, is basically the idea of trying to find the beta that, again, the concept trying to find the beta that minimizes our objective function or the error function. And so what we try to do is basically we try to find a beta, pick like a random beta that will result in some kind of error, and then we pick, and then we try to calculate the slope or the gradient of that line, of that error function line. And then move in the direction where the error will decrease on that graph. So if you imagine, like again, some kind of U-shaped graph that represents the error function, if our beta is like some like value above the minimum, then when we calculate the slope, then we can figure out the direction of that slope and move beta or adjust the beta such that the error will be reduced the next step that we go through. And so we keep on doing this. So beta n will turn to beta n plus 1. And we stop when the difference between the betas essentially is like 0 or a very small number, which means that we've converged to a point where the betas can no longer change or no longer decrease down, or the test error related to that beta will no longer decrease down that slope or gradient. So yeah, and we have to do this again just to emphasize it. We have to do this because there's no like real nice analytical solution to this, like in linear regression where we have the x transpose x inverse, etc. That was all nicely done for us. So we don't have that equation anymore, which is why behind the scenes when you run models using sklearn or equivalent, they'll be using some similar version of this in order to estimate the betas instead. So does that make sense to y'all? Any confusions or not? Cool. All right. So and then for the interpretation for the new model, it is basically very similar to the linear model, in that if we try to increase the one unit of, say, an x that's corresponding to a beta, instead of getting a beta change in y in linear regression, we're going to have some positive change in a logistic regression model. And the reason why I want to say positive instead of like an actual constant number is because that value will change depending on where x already is. So if you go back to linear regression, the relationship between x and y is essentially a linear relationship. This, the logistic regression model is not a linear, not a straight line anymore. So we cannot say exactly that if we increase by 1 unit, we'll change the response value by like 1 or 2 units. And so just to make that a bit more concrete, like for example, if your x was in the middle, then and you change it a little bit, then the probabilities would change much more than say the x was like on the ends, for example. So that's just like that's basically one difference in terms of interpretation, and so that lends itself to more of a more general view of how to interpret a logistic regression model, in that if the coefficient that you get from your model is positive and it is statistically significant, then basically increasing the x variable will increase the probability that something will happen. And conversely, if the beta was negative and it was statistically significant, then an increase in the x value will decrease the probability of something happening. And we'll see that more concretely when we run the model on the Titanic data set. Cool. Any questions about that? All right. And so before I go into actually running the model for you guys, one thing that we have to deal with, because the Titanic set and also data set and also the house price data set has this, are categorical data. And categorical data, just to remind you guys, are basically non-numeric data, so like strings, whether you're male or female, or where you live in this city or that city, etc. These are categorical data. And unfortunately for Python and most of the models out there, you can't really feed it strings of that nature. And to be honest, it doesn't really make sense either. For example, if you're trying to put these strings inside a matrix, it doesn't really make sense to invert like a matrix of strings. Generally, it does not make sense. So that's why like a lot of models, they prefer only numeric data only. So and one way to bypass this problem, in a very common way, is use something called one-hot encoding, which is a technique that I'll explain right now. So let's say, for example, we have the response variable survived and also a predictive variable called gender, which has basically essentially like two classes, male or female. We can easily convert this one predictor variable into two predictor variables, where each variable is essentially an indicator of whether or not that class existed in that original predictor variable's place. So for example, we can have a gender male column, which basically tells us whether a male like element existed in that spot. If it doesn't, then we have a 0. And if it does, again, we have another 1. And same thing for the female column. If we saw a female class, then we have 1 there. And if not, we have a 0 there. So we call these like dummy variables, but they're also referred to a bunch of other names too, like indicator variables. And this is basically the approach that you want to use when you're dealing with categorical data. And there's a function in Python that can easily do this for you, so you don't need to hard code it. Yeah.
2 questions. What would you do if you had more categories?
Yeah, so that's a good question. So you would generate basically n new predictor variables for n classes. So in this case, we have 2 classes, right? So we have two new predictor variables. Yeah, so there will be binary, right? The males will be 1s and 0s, the females will be 1s and 0s. So we have different classes will also be 1s and 0s. So it's really just an indicator whether something whether that class existed in the original column. or not.
So like you would add another column, like gender intersex or whatever, and then would you have like a 1 there if someone was intersex, and then
Yep.
a 0 and 0 for
Yep, exactly.
female?
Right. So basically, any class in gender should have a corresponding row on like in at least in just one of the columns that you just generated.
So would this be like we would want to make a new data frame or table with all of this if we wanted to like
Yes,
matplotlib on it?
exactly. But you don't have to do that by hand. There's a convenient function in pandas that basically does all of this dirty work for you. So it's basically one line, and I'll show it to you in the code example. Any other questions? Cool. All right. So, but there's still one actually problem with what I just said. We're not actually, in reality, we're not actually going to generate n new predictor variables. We're actually going to generate n minus 1. And can anybody tell me why exactly? And this has to relate to something that I mentioned last lecture, like towards the end of things. Yeah.
Well, I know for this case, it's because the two columns are correlated.
Yes.
If you're male, you're not going to be female.
Exactly.
So it's just arbitrary data.
Yep. You got it. So this is a problem of, again, multicollinearity, where if you have one column, you have essentially implied information of the other column. And so this will actually wreak havoc in interpreting your model and the coefficients that are produced. And so generally what you want to do is subtract a column. In this case, we'll just subtract one column. Say we just pick the female column arbitrarily, and we just basically have that column instead of the male column when we're feeding in the data. And this will like remove the multicollinearity problem. In general, it doesn't really matter which variable you kick out or keep. But for example, if you're in a business setting and you want to understand how a particular class behaves, whether a particular for example, if we have a variable on like different banks in America, and we're trying to predict like whether each bank will survive in the next 10 years or will it say or exist in the same year. Actually, that's not a good example. Let's see. Essentially, when we have a predictor variable with multiple classes and you want to understand how each class behaves, then generally you want to remove the column that you don't really care about. Or like, for example, one class will be unknown, then you can just remove that because you don't care how, usually you don't care how an unknown class will behave in compared to the other classes like male, gender, and stuff like that, or the bank name, for example. And so in terms of like predictive prediction though, it doesn't really matter. Cool. Any questions? Yeah.
So, what the last one is that again? Like, why is it 0 male and 1 female?
0 male,
Why is
1.
Why is 0 male twice?
0 male twice because this column is like an indicator column that's trying to basically put a 1 in the places where female exists. If you look back at gender, like we have male, female, male, the gender columns will look at that column and say, okay, male is not female, so I'm going to put a 0. Female is female, so I'm going to put a 1. And male is not female, so I'm going to put a 0. It's just an indicator like function that tells whether that class exists or not.
I actually think I know what you're asking though. You're wondering why there's two entries per male, right?
Yeah.
Yeah, so this is not a mapping. Like, think of the left side as a table. So we can have the first data point is one man who died, and then the second one is a female who died, and the third one is a different man who died.
But what's survived?
Survived? Oh, it's just, this is back to the Titanic data set. It's just a data point that says whether or not they like actually lived. They made it out of the Titanic.
Yeah, this is just basically copy from the Titanic. Yeah, sorry about that.
Oh, it's like true or false.
Yeah.
Yeah. Mm-hmm. Yeah, and then like in general, like it doesn't have to be like survived or not. It could be like red versus blue, but we're gonna encode it as 0 and 1 anyway because it's a binary type problem. Cool. Yeah. Get what?
When you're using the function in pandas, the
Mm-hmm.
does it take care of multicollinearity? Will it take care of the rows?
You mean the model, the actual like algorithm? Yeah. So if you run the model without like removing the columns, it will spit out something. Like it will keep all the columns and give you a beta. But but the p-values are going to explode, and it's not going to
Ask about the function get dummies.
get dummies. Oh yeah, so that's the function that we use for basically generating this type of matrix. And there's a parameter in get dummies that says I think it's drop first or something like that. You have to set that drop first to true, and it will drop one of the columns for you, or the first column for you. If you don't set that, then by default it will give you all the variables. So yeah, that's a good point. But I'll get to that very shortly. Any other questions? Yeah. What? Keep track of what? Wait. What do you mean? Uh-huh. Oh, it's so drop first will usually like take the first class. Oh yeah, that's a good point.
Can you like create a new data frame and like work off that and not change the original one?
So get dummies will create a new data frame for you. Yeah, I'll get to that in the code. But shoot, I forgot exactly how it picked the first class. For now, like when you run get dummies, like you can just look at which class probably disappears. Yeah, I have to take a look at that, like how it actually defines it though. But yeah, good question. Cool. Any other questions? All right. Okay, so. Back. All right, so if you go into the day 7 folder, if you can load, okay, there will be, again, an IPython notebook for you guys. I'm just going to create a new one for now. Let's call it Logistic Regression work. Oh, yeah, sorry. Yep. Okay, is that big enough? Yeah, okay. Regression model. Okay. Let me first import some things. I need pandas again. For as np. Oops. Oops. Come on. There we go. Pandas import different yeah, sorry. Okay, great. And what was it? Import. Okay. Wait, there was one more, I think. Oh yeah, is it from sklearn again? Crossvalidation import train test split. Okay, cool. All right, let's read in the Titanic data now. Read in Titanic. Oops. Okay, let's just call it that Titanic is equal to pd.read CSV data sets Titanic train.csv. Cool. All right, so we have our Titanic data now. We do ahead of that. We get this table that we should be familiar with. Okay, great. So as before, like I'm just gonna run a logistic regression model. Oh yeah, that was another thing that was missing. Oh yeah, I'm not missing that. Cool. Yeah, so we're gonna run a logistic regression on this, but a very, very basic one. So we're not going to deal with any feature engineering. We're just going to run get dummies in order to get our matrix that we want. our new data frame that we want, and also remove a couple columns that obviously don't really matter, like passenger ID, age, simply because it has a missing value, and we don't want to feed in missing values to our model. It does not know how to handle it, and also cabin over here. So first things first, let's remove a couple things. So Titanic dot drop passenger ID, age, and cabin. We want to set the axis equal to 1 for columns. In place is equal to true, and basically what in place does is that like normally you want to do assignment thing like Titanic is equal to that because Titanic dot drop will return a data frame, and so you need to like assign it to something. In place basically a shorthand of doing that, so you don't need to do the equal signs in the very beginning. So yeah, so that will be the output. If we do Titanic dot head again, we see that the passenger ID is gone, cabin is gone, age is gone. All we have left is name. Actually, yeah, let me get rid of name too. Let me get rid of ticket. And the reason is because the reason why I don't want to generate dummies from those columns is because essentially like each name is unique, and it will create an indicator variable for all whatever 800 names there are. And so that will be just massive, and we don't want to do that. And plus, when we're interpreting the model, like it doesn't really make that much sense to see if like if O1 existed, what would happen to the probability or something like that. And that's just like nonsense. Same with the ticket, and we'll keep the rest. So cool. And generally, like this format of just me like looking at the data and then figuring out like what to do with it. This is like should be your mind flow when you're like doing these types of or trying to like analyze these type of data and also run models. Is to like constantly look back at your data frame to see which one like what stuff you need to get done first and what more stuff you need to do later. So yeah, I forgot to drop the name in the tick column, so I'm going to do that again right now. Cool. And then, okay, so finally we can get our dummies data frame. So I'm going to do like Titanic, let's see, just basic for now. And then the function is called pd.getDummies. And what it takes in, actually, let's see, I'm trying to remember.
You should tab.
Oh. Hey, okay, great. So as Phil mentions, if you don't know what parameters it passes in, then do shift tab, and it'll do that for you. I did not know that, thanks. Cool. All right, so yeah, you pass in data first, and then you can ignore the rest except for, where is it? Columns, which are the columns that you want to get dummies from, which are basically the categorical variables that you want to give it. And then drop first, you want to set that to true for it to drop a column for you. So yeah, so let's get that started. Titanic, and then columns equals to, which one do we want? So P class is technically categorical because if you think about it, these are socioeconomic statuses. Like 1 represents highest level, 2 middle, and 3 lowest. You can like just put this as like a numerical predictor, like set that as a numerical variable. But that's like basically your type of decision that you have to do yourself. And the error or the accuracy that you get from doing validation method or cross-validation will tell you whether like changing it from numeric or categorical is a good idea or not.
There's actually like a pretty good notion of when you should actually do this.
Oh, okay.
So like if the data has like a notion of distance, so in this case actually P class does have a notion of like what is better and what is worse or something like that. So like 1 is probably more rich, 2 is probably less rich, and then 3 and so on. It would actually make sense to keep it in this categorical stuff. But if let's say these numbers aren't really related to each other, I actually explained this to Victoria at office hours today. But if they're not really related, you have a much better benefit for like making them, for actually one-hot encoding them, getting the dummies for them. Because basically the model that you're going to use is going to create like a internal representation of the distance between all these things. And so, yeah, That's basically it. If you want to learn more, just talk to me after class. Oh, what's up?
So you have to manually each time tell it which class, which columns or category variables you have to, I guess.
By default, it will choose all the categorical data for you. But it's always good practice to feed in the specific ones that you want, unless you have like millions of columns, and then you probably like hope that what you're doing makes sense. But yeah, it's for this particular data set. In most competitions, you won't have that many columns, so it's usually a good idea to just pick and choose, especially like in a business setting where you want like full control of exactly which columns you want to be converting to dummy variables. But if you have a lot and you don't really care about like pushing all of them inside and having a humongous dummy variable matrix, then the default is it will do it on all of the categorical data for you. Cool. All right, so so I'm just going to put p class in here, and then sex. These are numeric, and embark. I think that's the last one. So just 3 of them in here. And embarked. Oh yeah, and also just for your reference, embark is basically the town that they embarked in. So S stands for Southampton, C for Cherbourg, and there's supposed to be a Q here, but Q is for I think Queenstown. Oh yeah, and for the other variables, sib sp stands for I think the number of siblings the person had. Parch is I think the number of parents as well as children, perhaps. And yeah, I think the rest are self-explanatory. Does anybody have any confusions of what the variables mean? And usually, like on Kaggle, they will explain like what each variable stands for, so you don't need to like guess what it is. Cool. So there's that, and then what we want is to do drop first is equal to true. And we run that line, and then we get, so we do Titanic, basic, dot shape. Oh, is that right? Oh yeah, that's right. Okay, cool. So yeah, so what the getDummies function just did, it gave you a data frame back with the dummy variables that we wanted in the first place. As you can see, it chose to remove p class 1 and keep p class 2 and p class 3. For sex male, it chose to remove female, and for embarked, it chose to remove what was it? Which one is it? The C, the Cherbourg town. So and yeah, so we have a bunch of 1s and 0s. We have numerical representation of our categorical data. We are happy. We are set to actually feed this inside the model now. Cool. Does anybody have questions about that? That's basically like what you do for categorical data. So that would be something useful on the house price project. Anyway, so yeah, let's see. Let's put this into our local train and local test sets now. Test equals 2 Titanic. Okay, we use the function train test split to split our data frame randomly into train and test sets for us. We set the test size to be, in this case, let's choose 20% of our data. And what was let's see, random state. Yeah, great, thanks. And then since the splits are random, every time we run this line, it will give us different data frames. We want a random state, like say 1, 2, 3, for example, that will basically set the seed for us, the random seed. And so if we run this line again, it will keep on producing the same data frame back to us. So we run that line. We now have our local train, local test sets. And then what we want to do is now split these into local train X, local train Y to basically separate the X matrix that we had and also the Y response values into their own separate little data frames in series. And this is like just the natural way of feeding eventually, the reason why we do this is because the function that we're going to be using will require x on its own and y on its own. So local train survived. Local train x equals to local train the drop survived. As is equal to 1. Let's copy that again. And do this exact same thing for the test. Cool. And run that. We now have our local train x. If we do a dot shape, we can see its dimensions. We have 712 data points and 8 columns. For our local test, we have 179 data points to test with. So this is great. Now we can basically add our classifier now. That will be sm dot, I think it's logit. And then what we want to do is grab the y labels and also grab the x column with all our predictor variables into the same classifier. And then sm.logit will basically turn this into a logistic regression type model. And then in order to actually fit that, very simple, you do a clf.fit, run that line, and that's not an error message. Great. So this iterations, basically, they're using like the Newton-Raphson method again. It's like how many steps they've made during the iteration process in order to get our betas. So that's great. And then what we can do is now predict using that classifier. We do clf.predict and then feed in local test x, just the x's, not the y's. And what's wrong here? Not align. Shoot. Let me see. Okay, that's strange. All right, I'll think about that a bit later. I'll fix that later. Oh yeah, it's because of this. We want to do result is equal to, let's see. We want to save this as result first, and then threads is equal to result.predict equal test. Let's see if that works. Okay, yeah, that works. Okay, so my mistake was that clf.fit does not save the model for it. You have to save it into a variable called result. And then using result, you can it has a method called predict, where you can pass in the test x matrix for it to predict. So creds now, if you take a look at it, is basically an array of these numbers. And these numbers are bounded between 0 and 1, and you can interpret them as probabilities. Like this row has a 52% chance that this person survived. This one is 9% chance, 15% chance, et cetera, et cetera. So in order to assess our accuracy, we can essentially basically do this. Creds is greater than 0.5, which will basically turn our array over here into a vector of booleans, of trues and falses. So it's true if the probability is greater than 0.5, and false if it's less than 0.5. And once we do that, we can set that equal to our local test y series. And so even though this is a Boolean vector, internally in Python, it will understand that when we mean true, we mean 1, and when we mean false, we mean 0. And so we can actually do this equal sign and compare it to local test y, which has our 1s and 0s for our test set. Oh, whoops. And so if we do, let's see, mp.mean, for example, of that value, we have an accuracy of 80%. So anything that we predicted to be 0 and 1, we were 80% correct for the test set that we provided. I actually saw a hand up from there. Yeah.
Yeah, like as critical, SM the logit
Mm-hmm.
the train and train 1 and train X. And
Mm-hmm.
it actually ended up giving you like a canvas data class to numpy type of object value.
Let's see. Let's see. Line 16.
CLF equals SM.
So do you want to go up
Yeah,
and
I'll
like,
go.
fix that? Okay, great. Any other issues? Yeah. Or questions? I don't know if it actually uses that technique, but iterations is like the same concept in new-term absence. So, I am not sure of what the tolerance is, but I would imagine it would be some kind of low number. So that's something like you and I can search up after. Cool. Any other questions? All right. Yeah. So if we do this, this is basically our accuracy at this point of 80%, which is pretty good. But then let's see. What we can do next is, and let me see if I can get it out. Wait, no. All right, so within the regression notebook that is basically complete, I have something extra after we did these predictions, which is using, oh shoot, not this one. This one, okay. So that was just a basic model, and we got 80% accuracy, which is great, like so. But what else we can do is feed in the feature engineered and also the data clean data set that we did last week. So I'm not like gonna copy everything line by line because it's a lot of stuff. But basically, the concepts that we explored before, imputing the age, using the titles like Master, Miss, and Mr. Mrs. Also adding the cabin side feature, whether they came from the port side or the starboard side. Including the deck feature as well, which deck they belong to. The number of cabins per person as another feature. And basically, like these are just like steps that you take in order to grab more information from the original data set that you had and tacking them along as like feature engineer variables. And then finally, this line, get dummy variables, again, is getting the dummies from all the features that we had before. And notice that we have now cabin side and deck included to the number of the columns that we want dummies for. It's because cabin side, like starboard or port, is again a categorical variable, and so we want dummies for that. And same with deck, which ranges from A to G. It has I don't know, 6, 7. I don't know. You can count the classes, and so we get those classes for that. Let's see. Actually, let me try running this. I just want to show you guys what the new data matrix looks like. Okay, great. Okay, so yeah, so after we do some feature engineering, this is like the most like the best data set that we can format it with. So we have an age field column now. Again, we have the genders, number and group, etc. We have cabin side port, cabin side starboard. Oh yeah, and the reason why we have 2 here and not just 1 is because we technically included a 3rd class called unknown, and so it dropped the unknown class for us. And then decks B through G, as well as unknown. It got rid of deck A. So that's what the Titanic engineered data set looks like. And again, if we run basically the exact same lines that we had before, we will get an accuracy of 82.6%, which is an improvement according to the validation method. So this means generally that the feature engineering that we did and also data cleaning that we did help our model pick up more signal and increase its accuracy. You might not think that 2% is a lot, but in the Kaggle world, 2% means like can mean the difference between top 10% versus top 50%. So it will get to the point where like people's scores are so close to each other that like your model will like you'll need to constantly find very, very minute improvements to your data by engineering like probably one extra feature in order to get that small amount of improvement to beat hundreds of other people in front of you. So that is competition. Anyways, so if we do, okay, so we actually go back to our original model with our basic model and do a result.summary. It will output the coefficient, the betas, for each variable, as well as its corresponding p-value. And notice that not all of these are significant. So can someone interpret like what this line means? SIB-SP. It has a p-value of 0.008. What that means in terms of like significance. Like if you were to say to your boss, for example, give them like this table, like what will you say to them for this particular row? So this is back like an exercise in interpreting the logistic regression model. Yeah.
So I think it means that like it's a pretty important variable.
Right. Mm-hmm. Right. And so the next thing that you want to ask is what happens if we increase the number of siblings, for example? What would that do to? What does our model say that would do to the probability? Right. It's so it's not a hard question. Like, yeah. Yes, it would decrease the probability because the coefficient is negative and it is statistically significant. And so this kind of information is particularly valuable because like before you did the model, you wouldn't really have an intuitive understanding of like how the number of siblings would generally affect like someone's probability of survival. This basically will probably mean that the more siblings that you have, the longer it takes to get everyone together, and the more complicated and difficult it is in order for everyone to get on the same boat and to survive together. So that's like the story that you can generate from this model. But also it's still important, and this I didn't fix when running this model. SIB-SP and PARCH are actually correlated, so the number of parents that you have and children is correlated with the number of siblings that you have, which generally makes sense. And so in general, like it's okay if you like try to run a story on these values, but also make sure that there's to keep in mind that some of these columns are correlated, and that will like ruin some of the interpretation in the end. Fortunately, like these correlations aren't that great, but it's still something that like you want to look into, like remove one of the columns to see if that changes the beta coefficients of the other. And if it does, then like you generally want to remove that column and stick with the interpretation from the model that only ran on just one of the correlated columns instead. Does that make sense? Like when you have correlated data, like correlation of 0.3 or 0.4, it's generally okay when you see the p-values and to make up a story. But it's always like safe, good practice to rerun the model with one of the variables gone to see how the other coefficients have changed. And if they have changed drastically, then that means you want to get rid of the original interpretation you had before and just only use the interpretation or the p-values from the new model from the column that you just removed. So again, this is just like risky territory when you go about interpreting things. Anyway, so I do the rest. So fair, obviously, if you have like paid a lot, you'll probably be in first class, and so you probably have first dibs, and you're probably closer to the lifeboats. Males are very unfortunate. If you're a male, then definitely you have a much less chance of survival. And we saw that from our previous exploration of the data as well. And P classes, not too important, but again, these are correlated with fair, so we have to be careful of that. And embark, like which town you're in, it doesn't really matter, or at least according to a 0.05 alpha threshold. So yeah, that's basically how you interpret this. And then if we go down to our feature engineered model table, you start to notice that we have a lot more values to go through now. But essentially, we still have very similar stories. And then what's important is to see which features that you added are actually significant in the end. So, for example, how big your group is, which might be actually correlated with a bunch of other variables, is not important. But also importantly, which side of the boat you're in was very, very important according to the model. And so these kind of things, like when you're feature engineering stuff, you can always check to see if in the end the features that you generated did add some value to the model. Yeah.
We also use categorical ones, inbox Q, inbox S, inbox C, kind of the same meaning or whatever it was. Inbox S, it's not clarified, but it was closer. Would it make sense to maybe rerun it and separately or the other variables?
Yeah, you can do that, and it will spit out a different p-value, and then you can see what that p-value is. So, did that answer your question?
Yeah, I'm just wondering if like you ever have to do that, right? Or is it kind of
Sometimes it's usually only like variables that are a primary concern for me. For example, for whatever reason, like I'm really, really interested in these classes and how each one of them affects the response. Then like I like juggle a few things to see, to make sure that what I'm seeing is actually true. And then for in the Kaggle space, I really don't care. So it's all about the accuracy, final accuracy in the end. In fact, like oh, let me show you guys. Actually, let me show you guys what happens when we don't do a important step. Hold on, let me see if I can find it. Here. So remember when I told you guys that generally we want to set drop first equals to true, and then I'm going to show you guys real quick what happens if we set that to false. Just to reiterate my point. Okay. All right. So this is the. Let's see. Is that the right thing? Oh no, I didn't make that. Okay, great. All right. So this is the new model. We basically have gibberish. It will just not produce anything for you if you don't remove that column. So again, this is just a warning that you want to drop the first column. Otherwise, this is meaningless. But you do get an accuracy. See, 81%, which is actually a little bit higher than before. So again, this is like trade-offs between interpretability and your performance on Kaggle. Anyway, so any questions? That cool. All right. Yeah, I'm not going to do that for that. Feature engineered. Okay, that's good. That's good. That's good. Okay, cool. Now we turn to cross-validation. All right. So great. So for K-fold cross-validation, this is. Can you guys see that? Is that? It looks very grayed out from my perspective, but can you guys see that?
Oh, yeah.
Is there a way to do that? All right, cool. All right, so the reason why I'm introducing like a new way of testing things is because the original validation set method that I introduced on Monday, while it is fast and very easy and intuitive to understand and run, it is sometimes it will essentially be a little bit unstable in the amount of error that it will like spit out for you. And that's like that, and that's because of two main reasons. One is that essentially, since we're doing random slits of data, you will always get a different accuracy every single time you run the validation set method, and that's why we need to set the seed in order to have consistent results. The other reason is because, well, if we're running a validation set method, we're only training on, say, 80% of data or 90% of data. It is not 100% of the data. And so the error that we get on our local train set would generally be an overestimation of the error that we will actually get on the Kaggle leaderboard. And it's because we're using less data, and generally less data will make our model less accurate. And again, like the more data we feed into a model, generally the more accurate it will get, and the more it will converge to the actual test error on the test set. So when we are splitting based off the 80-20 rule or 90-10 rule or something, we're basically feeding it less data, and so it have less data to work with. And sometimes it is statistically possible where the 80% or 90% of the data that you train on will be vastly different from the 10 or 20% data that you would test on. So that's another cause of concern. And so that's why we have a slightly different method that will take slightly longer, but is a bit more powerful in getting you more accurate results. And this is the K4 cross-validation method. And this is, and I like to think of it as like validation set method on steroids, because we're doing validation set method multiple times, but in a very controlled way. And so this infographic basically tells you exactly how we will split the data set. So using the full entire training set, we're going to split using, so assuming that K is 10, we have 10 folds. We're going to split our data into 10 different folds. We're going to pick 9 of those folds as our training set and pick 1 of those folds as our test set. And that will be basically 1 iteration of our model and 1 accuracy score from that run. The second time around, we're going to pick a different set of 9, and then we're going to use a new test set, basically, from another fold to get our accuracy from that run. And we're going to do this again and again until every single fold gets a chance to be tested on. And so using this way, we actually get a mean, if we compile all the accuracies, we get 10 different accuracies. If we take a mean of that, then we get 1 final score. And this is generally a preferred way of doing a model validation method so that you can get the most accurate sense of how well your model will perform on the real test data set. Granted, it will take a bit longer, but in general, this is what you should be doing if you're, for example, trying to make sure that you won't move around too much on the private leaderboard when that gets released. And yeah, so does anybody have questions on this particular concept of what we're actually trying to aim for here? No? Cool. In that case, these are the names that have been submitted to us. If you do not see your team name, please send it to us. We really want to have that down. And also, some of these names are very creative too, so that's more fun for us. Is there anything else?